These are the answers to the previous section. Hopefully you got them all correct. A calorimeter is a container and it holds a reaction mixture with a lid, and it keeps any heat that's being produced from leaving to the environment before you can measure it. In general chemistry, we actually do use coffee cups and lids with a thermometer going through the top as a calorimeter. Then you measure the heat transfer by measuring the temperature change before and after you combine the materials. Let's look at these two problems here. Think back to your specific heat capacity. We're going to compare 1 gram of copper with 1 gram of gold. They each have a C value, which is the specific heat. Notice it's a little c. For copper, it's 0.387. For gold, it's 0.129. Which one has more released as they cool from 100 to 90 degrees Celsius? That C value for copper, what it means is that for every 1 degree Celsius, we have a joule, not just 1 joule, we have 0.387 joules released. Then for gold, we have for every 1 degree, 0.124 joules released. So gold has less energy released per degree Celsius. So that our range is 10 degrees. So over the course of 10 degrees, the copper will release 10 times 0.387 or 3.87 joules. And the silver releases 1.24 joules over that 10 degree range. So copper has released more energy, but also when we are looking at comparing the two when temperature increases, that means that we need to add in 0.387 joules for copper per degrees versus only 0.124 joules. This next problem looks at water's specific heat capacity being 4.184. How does that compare to most metal heat capacities? Look in the problem above. Do you see how in the earlier problem they were in the decimal point range, whereas water's in the ones position? You'll notice that this happens for most metals. We have a table you can reference in your textbook. You'll notice that most metals have a heat capacity below 1. This makes them great conductors of heat. In most cases, they are at least a factor of 10 smaller than water. Besides water's abundance on Earth, how does this higher heat capacity make water a good substance to cool hot metals and reactions? Water-specific heat capacity says that you're going to have to add in 4.184 joules just to get the water to change upwards by 1 degree. We just saw that copper will release only 3.87 joules as its temperature decreases by 10 degrees. It still will not have released enough energy to raise the temperature of the water by 1 degree. So metals will decrease in temperature by 10-12 degrees before enough energy has been added to the water to increase the water's temperature by 1 degree. We're going to look at this again in the next problem. Assume you have 1.0 grams of iron and 1.0 grams of water, so they're the same amount. Iron's specific heat capacity is the 0.449, water is 4.184. How many degrees will the metal's temperature drop before the water's temperature changes 1 full degree? These are the best pictures I could find to illustrate what's going on. We're going to make the circle iron, and we're going to write iron and its specific heat capacity in both circles. So there's the iron and there's the 0.449. Now we're going to make sure that it's surrounded by water in both cases. I want the temperature on the left to be measuring the iron, so we're just pretending there's a way to incorporate this temperature measurement into the iron. And I want to make it very clear that the other thermometer is measuring the water around the iron, not the iron. So from the last example, you should expect that the hot iron is going to start at a high temperature and decrease in temperature, and that the cooler water is going to start at a low temperature and increase in temperature. We're going to zoom in on this thermometer touching the iron. Let's say that it's only at 100 degrees. As it goes down by 1 degree, it releases 0.449 joules. Each time it decreases by 1 degree, it goes down by 0.449 joules. The question asks to determine how many degrees will the metal's temperature drop before the water's changes by 1 full degree. So let's make sure that we're seeing that we want the water's temperature to increase by 1 degree. And we know that it will take the specific heat of water, the 4.184 joules, to increase it by 1 degree. So looking at the metal, we're going to decrease that temperature. We've taken it down 1 degree, 2 degrees, 3 degrees. Let's take it down several more degrees. So this temperature has decreased by 9 degrees. Here's where it would be at 90. That would be the 10th degree. And so only when it has gone down by 10 degrees will our total joules released equal 4.49, which will be more than enough, by just a little bit, to decrease the water's temperature. There's a mathematical formula that helps us determine these changes without having to draw pictures and without the masses having to be the same amount.